This is Brantley Kearns. My presentation is on fast radio bursts and magnetars. Mm, Neutron stars are stellar remnants that can exist in a variety of different forms. Pulsars make up the majority of observed neutron stars. They are highly magnetized, rapidly rotating neutron stars with a lighthouse beam of radiation that produces pulsed emission. They can rotate at a variety of speeds, the slowest observed being one rotation every 8.5 seconds, to the fastest being 716 rotations every 1 second. These faster pulsars are often known as millisecond pulsars. Their magnetic fields range from 100 million times to 1 quadrillion times stronger than the Earth's magnetic field. Magnetars are another rarer type of neutron star. Their magnetic fields are immensely strong in the range of 10 to the 9 to 10 to the 11 teslas. Earth's magnetic field is only on the order of 10 to the negative 4 teslas for comparison. They are the strongest known magnets in the universe, and some magnetars are also pulsars. Much of the formation of magnetars is still largely unknown. One of the most recent and promising theories is the case of stars in binary systems. When one of the two stars in the system enters the red giant phase, the material begins to transfer to the smaller star. This causes the smaller star to become larger and spin more rapidly due to the law of angular momentum. This process then causes some material to be sent back to the first star. This essentially rekindles the first star, though now the second star has become too massive and begins to collapse. This supernova then ejects the first star from the system. For the second star, due to its new mass, we would expect it to turn into a black hole. However, due to the binary interactions and high rotational forces, the star's magnetic field has been amplified on the order of thousands and creates a magnetar. Other theories suggest that magnetars can be created in a supernova where the temperature, magnetic field strength, and spin are in some kind of Goldilocks range in which a star that should have collapsed into a black hole instead becomes a magnetar. When matter is exchanged from the larger star to the smaller star, like the image on the left, the material will begin orbiting around the smaller star and will eventually begin to accrete onto it. As we all know, when a figure skater puts her arms out and then brings them in, her spin increases. In the same way, as the matter falls onto the star, the accretion disk is reduced and the star's spin increases. These two pulsar types are actually one and the same, but are different phases on a magnetar's evolutionary track. It exists as an SGR pulsar for the first 10,000 years, and then it recedes into an AXP pulsar for the rest of its lifetime. A soft gamma ray repeater, or SGR, is a pulsar visible in regular light and repeatedly emitting bursts of soft gamma rays, as the name suggests. It eventually exhausts its properties and goes into the next phase as an AXP. The image to the left is an actual observation of an SGR pulsar. SGRs are persistent X-ray emitters around 10 to the 35 ergs per second. They also exhibit persistent pulsation every 5 to 10 seconds. They have huge spin down rates around 10 to the negative 10, which means their spin slows down very quickly. And of course, they produce frequent soft gamma ray bursts. This plot shows one of the many short duration bursts of hard X-rays that SGR emits. As you can see, the y-axis represents the pulse count per 0.5 seconds, while the x-axis represents time in seconds. Another type of magnetar is known as an anomalous X-ray pulsar, or AXP. Once a magnetar exhausts its properties as an SGR, it becomes an AXP. It begins emitting its light and X-rays and can only be seen to us in the X-ray range. The image to the left shows the ejecta from the supernova in the visible light. The circle at the center shows the location of the AXP that is emitting in the X-ray range. AXPs are also persistent X-ray emitters between 10 to the 34 ergs per second to 10 to the 35 ergs per second. They also produce the same persistent pulsation as SGRs. They have a larger spin down rate at 10 to the negative 11 and show no evidence of having a companion star. This plot shows the persistent pulsation exhibited by AXP pulsars. The y-axis represents the pulse counts per second, and the x-axis represents time in hours. This plot shows the relation between the period p and its time derivative p dot for various pulsars and magnetars. Magnetars have a higher spin-down rate, meaning they slow down faster than regular pulsars due to their high dipole magnetic fields, and they have longer periods. You can see that both types are grouped at the top right corner of the plot due to this commonality. Due to this dipole radiation, most magnetars end up with a spin rate around 1 rotation per 8 seconds. As shown, the magnetic field configuration in the magnetars changes with radius. In the center of the magnetar, the magnetic field is extremely intense. That strength falls off towards the surface of the magnetar. The structure of a magnetar is still highly theoretical, but there are some parts which scientists are fairly certain. The outer crust is made of ions and electrons, while the inner crust is a bizarre ion lattice soaked in superfluids. In the core, it is believed that there is an outer core of superconducting protons, and the inner core is still unknown, but is thought to possibly be some type of ultradense matter in which the neutrons and protons may either remain as particles or may become a soup of quarks or hyperons. From hours to days since the birth of a magnetar, the interaction between the magnetic field and surrounding plasma pumps the brakes on the star's spin rate. The interaction pushes out a bubble of plasma that then interacts with the original supernova shockwave. This is the cause of the double peak in blue in the magnitude, shown here. The first being the supernova and the second being that of the plasma interaction. Sometimes there will be only a single peak, and that is due to a less intense magnetic field which allows the spin to decrease more gradually, so the plasma bubble interacts sooner and the supernova and plasma interaction peaks together, in black here. This is a visual representation of what I just said. A decelerating magnetar drives two opposing fast-moving bubbles of hot plasma from its magnetic poles. A few days later, the bubbles collide with the supernova blast wave and generate a second peak in the brightness. The magnetar's magnetic field evolves as shown here. The spin evolves over time as shown below, where the subscript 0 denotes a quantity measured at the time of the birth of the neutron star. Since p dot is proportional to omega dot over omega squared when n is less than 2, it implies that p dot increases over time for a constant magnetic field. When n is less than 1 or alpha is less than 0, it implies that the spin goes to 0 in a finite time. Starquakes triggered on the surface of a magnetar disturb the magnetic field that encompasses it, often leading to extremely powerful gamma-ray flare emissions. The largest known was from SGR 1806-20 and emitted more energy, which lasted only a tenth of a second, than the sun will emit in 150,000 years. A magnetar's surface, due to the immense gravity, is so flat that the highest elevation is about 10 centimeters. Despite this fact, they rarely form a perfect sphere. Due to the rapid rotation experienced by a magnetar, the crust tends to bulge around the middle. As the spin slows down, the field becomes a bit twisted, and the only way for it to untwist is to break the crust and reconfigure it. This breaking is known as a starquake for obvious reasons of its similarity to tectonic dynamics on Earth. In the image to the left are a series of gamma-ray flares expelled by a magnetar called SGR J1550-5418. These flares are thought to be from a starquake within the magnetar. The rings are made when the X-rays interact with the surrounding gas and dust. The plot below shows the time-resolved spectra of SGR J1550-5418 during one of these burst detections. The y-axis represents the number of counts, and the x-axis represents time in seconds starting at the initial trigger of the starquake. Essentially, FRBs are brief radio emissions from distant astronomical sources whose causes are only theorized. It has been confirmed that at least one of these emissions came from a magnetar, but all other emissions are of unknown origin. These are very recent discoveries, the first of which was discovered in 2007. Only 32 more had been discovered by 2017, and since 2018, and after upgraded equipment, another 47 have been detected. As shown in the figure on the left, an FRB is detected. The difference between this detection and other sources of radio waves is the sudden spike in radio waves. It is also significant how brief the detection is. Scientists have only made a small number of these detections, and many of them have only been detected from a source a single time. This makes it very difficult to determine its origin and the mechanisms that cause it. This is the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, a revolutionary radio telescope located in British Columbia. It began operation in 2017 and is a large part of the increased FRB detections. FRBs are brief energy radio wave detections that originate far across the universe. At least 3 are known to repeat, but most of them are single events. The leading theory is that a magnetar releases a flare of electrons and other charged particles, as shown here. Then the flare collides with the remnants from an old flare, creating huge magnetic fields. In the shock of that collision, the vibrating electrons generate energetic radio waves, and as they slow down, they shift to lower frequencies, which is what we pick up on our equipment. There are many theories about what these FRBs might be. Some scientists think they could be from interactions that take place in active galactic nuclei between a black hole and the gas and dust around it. Others think they could be from either collapsing or merging neutron stars. However, these theories have a flaw because they would only work for single event FRBs. Still, others think these emissions might be from newly born magnetars. Again, this is flawed in that it doesn't repeat from the same source. And of course, the most unlikely theory, the one that also seems to get thrown around when new phenomena are detected, is that it could be from some intelligent life. Some think that a sort of extraterrestrial solar sail spaceship, which are not that far away from being built by us, might produce these emissions, though I doubt anyone takes this theory seriously. These are my references.